Okay, welcome to class, everybody. For those of y'all online, if you happen to watch the videos, I should have sent an email earlier this week, but I don't remember if I did or not. So, just a reminder for everybody online and in class that the chapter 5 and 6 homework will be due Monday. It is up on Canvas, and we will have the chapter 5 and 6 tests on Monday. So, make sure you're getting your homework done over the weekend if you haven't started and getting prepared for the chapter 5 and 6 test. And then you'll have next week to finish up the plate tectonics lab as we work through this next chapter after volcanoes, which should be, I believe, geologic time. Is that right? Let me grab my pen. We can find out. We have the power. What was it? G.I. Joe? Knowing is half the battle. Yes, geologic time is next. And then we leave behind rocks and the earth. Well, not the earth, but we go into the wonderful, somewhat boring world of oceans and water and atmospheric stuff and weather. And that's where we will end the semester on, which is nice. This is week 10 out of 16. So after this, we have 5 weeks left. Minus 1 week for Thanksgiving, which I'll probably still give you a couple, assignments to work on, maybe some homeworks, but nothing crazy for sure. Maybe maybe that's a good time to get going on the next lap. We'll see how it actually comes out. This week's the last week of October. Thanksgiving is what, the fourth Thursday? Is that how we do it? 26th? Yeah. It says usually most calendars tell you what day Thanksgiving is, Mr. Bailey. You don't have to ask. So let's pick up where we left off yesterday with the incredible Jeep outrunning a pyroclastic cloud. So as I told you, I'm pretty sure I looked it up one year. I couldn't find it this year, but pretty sure the Jeep people lived. If the Jeep people didn't live, then the person taking the picture probably didn't live either, and then the image would probably be ruined. And so let's just assume that everybody lived here. Maybe it was towards the end of the pyroclastic flow, and it kind of died down a little bit, and everybody left unscathed. That's nice to think about. So the next slide we leave off with that we didn't cover yesterday is the actual slide for pyroclastic flow. A pyroclastic flow, or nuit ardente, which I guess would be French. Ardente definitely sounds French. Is a hot volcanic gas infused with incandescent ash. What does incandescent mean? Yeah, like it's so hot it's probably glowing. Like an incandescent lamp is like a lamp that gives off light. So probably hot enough to nearly be molten fragments of ash and lava fragments. Very, very fast, gravity driven, can move up to 100 kilometers per hour. It probably slowed down by the time you got the Jeep picture, because I don't know that a Jeep would be able to outrun it. But yeah, very, very fast. Fast enough to knock down all the trees in the video that we saw the other day on Mount St. Helens. It is a low density cloud of hot gases and fine ash on top of a layer of vesicular pyroclastic material. So there's also bits of rocks and lava and other things in there. And it's caused by the collapse of the eruption column. So you have the big plume of gas that goes up, and part of it actually gets pulled down due to convection cycles and due to gravity, mostly gravity driven because you have some heavier pieces there. But it starts to collapse down and run down the side of the hill and knocks down everything in its path, leaves ash layers behind. It's pretty destructive. Outside of the lava or the actual explosion itself, this is one of the more destructive things in a violent volcanic eruption. So here's an image that shows the destruction of a town because of a pyroclastic blast. So this was the town before the eruption, a 1902 eruption in Saint Pierre near Mount Pelée, which I believe Mount Pelée is it Peru or Chile? Somebody Google it for me, please. just so I know and I get it right next time. Mount Pele.
The Caribbean?
Oh, in the Caribbean? All right, so not on the mainland. That would make sense. You have a nice bay here, so it being an island one. Does it say what like island it's in?
The Caribbean island of
Martinique. All right,
Martinique.
all right, all right. I've never been there. I've actually never been out of the country, but I've heard Martinique is one of the like nice Caribbean islands. Martinique or what are the other ones? Anyways, I can't remember right now. But yeah, that's a nice vacation destination. Although you'd hate to be vacationing there in 1902 when Mount Pele erupted, because you can see the before and after destruction, and like literally everything's gone. The entire town, many houses were here. You have lots of docks. Look, all the docks are just gone, wiped out. The houses, like you can see some structures, every single roof is gone. It's just complete devastation. Um, it's pretty crazy to see. So these are very serious events when you have a large, violent pyroclastic cloud coming down the side of your volcano. Now, moving on to lahars. Lahars is a term to describe a mud flow of water mixed with ash. Usually the water comes from glaciers or snow melt on top of the volcano just before eruption, and the heat of the lava and the eruption itself instantly melts the ice and the snow and causes it to mix with the ash from the volcano, and it flows down hill in a very violent manner. Usually these floods are very extreme, and when they settle down at the bottom, depending on the mixture, they can turn into like cement like hardness, because you have a lot of ash mixed in with your water. It can harden very quickly and somewhat permanently, very difficult to dig things out. So you can see here, this is a person for scale. You have very large trees kind of thrown into this river here, and you can see how high the lahar was at its peak. You're probably talking what, at least 30, 40 feet above where the person's standing, which is not even, the same level as the water level in the river. And so this was a pretty crazy flood for this area. So that is lahar. Know that it's ash mixed with water, and other pyroclastic materials, and it happens pretty quickly and pretty violently. And they say can occur with dormant, extinct volcanoes because those are the volcanoes that get a chance to build up a lot of ice and snow at the peak or in the crater. So, and actually, when I tried to look for the bulge in Mount St. Helens the other day, all I could find was articles from about 4 years ago, maybe, about a glacier forming in the crater of Mount St. Helens, and they were like, "That's not good because even if it does a small eruption, that glacier is going to melt very quickly and cause a lot of problems." So they go through some other volcanic hazards. Ash is a big deal. Next semester, when we talk about volcanic hazards, we will talk about the Icelandic volcano that had ash clouds going over Europe for quite a while and disrupted a lot of travel and air travel patterns and cost their economy quite a bit. They can damage buildings, living things, aircraft engines. It just kind of gets everywhere and isn't very good for anything. Sulfur dioxide released into the air affects air quality and creates acid rain. Also not good. The good news, if you go back to the slide where they give the breakdown of the gases that come out of a volcano, typically sulfur dioxide is not one of the most abundant ones, although it doesn't take very much to be in the air to kind of cause adverse effects. So kind of a mixed bag there. Tsunamis can be created when your volcano collapses. So if you imagine Mount St. Helens, like the entire side of the mountain caving down and dropping off like 1,000 feet from the peak, if that volcano were right on the edge of a lake or some sort of body of water, and it falls into the water, that's going to displace a huge amount of water and create a very, very large wave. In fact, one of the largest tsunamis I think we've ever not recorded but discovered was because of a collapse of material, like the hillside kind of fell in. I don't remember if it was an earthquake or a volcano, but it caused like the largest wave we've ever discovered. I watched a little thing on that. It was pretty interesting. And then atmospheric cooling. So ash and aerosols can reflect solar energy and kind of bounce that energy back out of the atmosphere and cause cooling on a local and a global level if there's enough volcanoes kind of happening at the same time. That being said, the gases released can also have the opposite effect long term. You can be releasing a lot of greenhouse gases into the atmosphere. The ash won't stay up there forever. And so when the ash is gone, you still have the greenhouse gases, and they're going to cause a warming effect as well. So they give you another little breakdown of some of the parts of the volcano and the pyroclastic flow, along with some pictures. They have volcanic ash destroying plant life and can be drawn into the lungs of humans and other animals. And also, obviously, the animals graze on the plant life, so that could be double bad for them. Ash and other pyroclastic materials can collapse roofs or completely cover buildings. Not 100% positive, but I guess this house would probably be in Iceland. And that is an extreme amount of pyroclastic material. People in the north think they have it bad when they have to shovel snow. Imagine having to shovel like thousands of pounds of rocks away from your house, or just abandoning your house altogether. And then lava flows can destroy homes, roads, and other structures in their paths. So this person, probably in Hawaii, is not going to make it to work on time today. There's a lava flow blocking their path. Unless they had a Jeep, then they could just drive over the lava flow and it wouldn't be a big deal at all. That's obviously a joke because bad movie. Did I talk to you about the bad movie, or was that the other class? You got to watch it. If you're into bad movies, it's what's it called? It's a Pierce Brosnan volcano movie, and it's terrible. Dante's Peak. Yes, Dante's Peak. No. Rewatch it. It doesn't hold up. You'll be entertained for sure, but it's not a great movie. There's not a lot of Pierce Brosnan movies that hold up over time. When he was Bond, everybody's like, "Yeah, Bond movies," and then now you watch one of them and you're like, "Oh, this is not a great movie." Although I will say he played a great bad guy in Mrs. Doubtfire. So there you go. But yeah, in that movie, he like drives a Jeep over like a like river of lava, and they're like, "Yeah, we made it." And I remember one of my college professors just like yelling about that in class. But maybe the rest of it, it's not like Journey to the Center of the Earth or anything. So maybe the rest of it was somewhat accurate. But I was going to say something else about Pierce Brosnan, but never mind. So this is a nice little diagram here. You have your volcano erupting. You can see the lahar flow kind of coming down. I don't know where this is pointing to. They're saying that's lava flow. Lahar flows right here. That's what I was thinking. So your ice melts because of the lava and the eruption. It flows downhill in a very quick manner with your ice mixing with your ash and dirt and creating a lot of problems. You have your lava flow. You have your eruption column going up and your pyroclastic flow coming down. Your eruption column can bring down bombs and blocks and other bigger pieces that kind of get erupted up into the air. And then your ash and your sulfur dioxide can create ashfall and acid rain, which can be a pretty bad thing. Also, you can have a collapse of part of your mountain, which can create tsunamis if you're near water. So, nice. All right. Now, how does a caldera form? So remember that a caldera is a very wide crater at the top of a volcano. Usually, it's going to be a shield volcano, but not always. If you have a very large volcano, you can have a large crater, and we call it a caldera. And so they give you kind of a sequence here. Basically, as your volcano's erupting, your magma chamber's full. There's lots of pressure which is pushing the magma up to the surface, causing your eruption. If you have enough drainage of your magma chamber, it doesn't really like empty out, but you lose a lot of that pressure. You've now weakened the ground above it, and you start to have collapse of the ground above it down into the magma chamber. So everything literally like drops down. And you can see this might be an extreme example, but your entire volcano here has kind of dropped down into the earth. And so what used to be almost the entire volcanic mountain is now just a huge crater, larger than less than 1 kilometer in diameter. No, it's larger than 1 kilometer in diameter. Less than 1 kilometer is going to be just a crater. So I need to go in and change that. But yeah, you can see that's going to be bigger than 1 kilometer. It's the entire volcano. So it collapses down, and then once the volcanic activity dies down, water is going to naturally fill it in, and you get some really nice lakes in there. I've heard that this is literally one of the nicest lakes and places to visit in the United States. It's not super accessible because it's on top of a mountain. I don't think like the entire mountain collapsed in. I think it's up towards the top. But you can look this one up, Crater Lake. I believe it's somewhere in the like northwest of the United States. I'm thinking like Oregon or like Utah or Nevada or something like that. Oregon. All right. So yeah, it's in Oregon, and I've heard it's like incredibly beautiful to go and visit. So if you're ever in the area and you have time, be like, let's go visit Crater Lake. So now moving on to fissure eruptions, basalt plateaus, and flood basalts. Fissure eruptions are basically where you have lava coming out of a crack in the ground. Fissures are fractures or cracks, and it gives a release of the pressure, and lava just kind of flows out of it. So you can see this is not like a full volcano. It's literally just a crack where lava is being emitted. These are actually pretty common in Hawaii because there's lots of lava or magma underneath the surface, and it doesn't always find its way to the traditional neck of the volcano to come out. If it finds a little fracture, it will go up through that and come out onto the surface. And the problem with these is they can open up kind of anywhere and ruin our roads or our houses and cause a lot of issues. Basalt plateaus are flat, broad accumulations of basalt emitted from fissures. So you have a lot of stuff coming out, and it kind of builds up a large area of basalt. Like over here, they're going to call this like a basalt plateau, kind of being up above everything else, like over here. And then flood basalts is molten lava having flowed long distances within a basalt plateau. And I actually want to show you, well, let me make sure there's no image. There's not. So let me go back. I want to show you real quick what a flood basalt looks like in a major term, because we have flood basalts from the last eruption of the Yellowstone supervolcano. Green River flood basalts. If you look up Green River flood basalts, I believe that's what it's called. Yes. And so the last time the Yellowstone supervolcano erupted, so here they talk about the Yellowstone supervolcano. They have the Columbia River flood basalts. Let me change that. My bad. Columbia River flood basalts. They basically extend all the way from the Idaho area all the way to the Pacific Ocean. They go over Oregon and Washington, the entire width, all along the Columbia River. This is a major flood basalt area. And so you can just see the magnitude of how much material was put out here. That's actually pretty cool. They have the columnar joints. So this would have been magma that piled up pretty thick and then cooled. And as it cooled, it contracted, and it got these really geometric type joints in it where the rock has been fractured as it shrinks down. Almost like mud cracks, but much deeper. So Yeah. What is this? Different eruptions. We got different dike swarms of different lava that's kind of come out. And so these, with all this material, these are more than likely associated with the hot spot that is now underneath Yellowstone. Wonderful. Wonderful. So, flood basalts. Next, we talk about volcanic necks and pipes. Volcanic necks are going to be your conduit. So, they have a pretty good image here illustrating what we have. We have an old volcano. It's piled up with lava and ash and alternating layers. And you have your neck where your lava comes up and feeds the volcano for its eruptions. At some point in time, the volcano dies out and goes dormant or extinct, actually, not dormant. The ash and the lava here are going to be much more susceptible to erosion and weathering. And so literally the entire volcano just gets weathered away and moved somewhere else in small little pieces. And what's left is this very hard protrusion of your igneous lava rock, which was kind of sheltered from everything else, and it's still sticking above the ground. And so they have this example right here, which is called Shiprock in New Mexico. You can go and visit this, and I guess if you're a seasoned rock climber, probably make it up to the peak, which is 1,380 feet, which is probably a decent climb. But yes, this is an old volcanic neck, so you'll literally be standing like in what was the middle of a giant volcano, probably a decent time ago. They don't give any dates on these. But yeah, volcanic necks. A pipe is a volcanic neck that carried magma from the depths more than 150 kilometers below the surface. So they're both very similar kind of features. Now, intrusive igneous activity. So this is going to be igneous stuff that never actually makes it to the surface. You have intrusions or plutons. I've already talked about plutons. Those are going to be your lava lamp kind of bubbles of magma that comes up beneath the surface. They can be exposed if they get uplifted or eroded away, like the one in Enchanted Rock down in central Texas. Or they can kind of always just stay underground if they're never exposed or have the rock above them eroded. We also have intrusions, which are going to be, well, intrusions can also be plutons, but they have different types of intrusions. We have tabular ones or massive ones. The massive ones are going to be your big plutons. The tabular ones are going to be ones that kind of run off to the side. And we have two different terms to describe them: discordant or concordant. Concordant is going to be ones that kind of go along with everything else. They inject parallel to features. They may be harder to kind of see because they just look normal in everything else. Discordant is going to cut across everything else. It's going to ruin all your nice, pretty layers and kind of mess everything up. So they have some nice examples here on all these diagrams. There we go. I lose that word often. So here's your plutons underneath, causing your magma chambers that feed your volcanoes. As the magma chamber expands and comes up through the surface and pushes all this rock to the side, you have a lot of fractures and faulting, causing a lot of areas of weakness that the lava can go up and intrude into. So if it's a vertical piece, and we'll get to these on another slide, I'm sure, but if it's a vertical crack where lava flows through it, that is called a dike. And so a dike is what I was referring to when I was talking about rock wall yesterday. And then if it's a horizontal crack where the lava goes through and it fits in between different layers, but it's nice and horizontal, that's going to be called a sill, like a window sill is nice and flat. A lava sill is nice and flat. They have the pipe of the volcano. They have some cinder cones over here. Your big, they don't have them over here. They'll have them on another page. Your big, large intrusions underneath here are going to be called batholiths. The smaller ones that kind of push up the land around them and maybe have flat bottoms are going to be called laccoliths, which are weird names. They almost sound like Klingon, but there it is. And then they have a little fissure eruption over here. And then after all the the igneous activity dies down and it loses temperature and it solidifies. It all kind of gets locked in place underneath the surface. And so your magma bodies cool down. You still have the dikes and sills that are running vertical and horizontal. Your old fissure eruption is now a dike sitting above the surface, which would be like the rock wall in Rockwall. And you have a little hill here that's eroded away and left your laccolith, so you can have a nice igneous kind of rock formation or hill or mountain out in the middle of nowhere where it doesn't really look like it belongs, but it does. So yes, your batholiths are going to be your very large pieces of your magma chamber, the big type of rocks that all just kind of fill up because of your lava. So once they get exposed, they're called batholiths. Now, your different type of intrusive bodies, and I said they have another slide on these. Tabular ones are going to be like flat, like tabs. And so we have two different types, dikes and sills. Dikes are discordant, and they cut through everything. They cut through all your layers. They're usually vertical or at an angle. Sills are going to be concordant. They're going to come flat in between different layers. And so just looking at this in a picture, if they didn't kind of have it highlighted here, it just kind of looked like another layer. It wouldn't be until you went in and saw, oh, this is like a very hard volcanic rock and not a sedimentary rock like literally all the other layers above and below it. That would tell me that something weird happened. So I would know that it's a sill and not just another sedimentary layer. And if it's vertical, you can see that it's not being eroded the same as everything else. It almost looks like a hill that people have piled up here because it's kind of protecting the sediment on either side of it. And so that's a nice dike there. And you can see right next to a volcano. So the volcano has allowed that crack to happen or forced the crack to happen, and then the lava kind of released itself up into that crack, causing the dike. Now, columnar jointing. I showed you this in the Columbia River flood basalts. And basically what happens here, it's just like mud cracks. When you see mud cracks in Texas, it rains, everything swells up because the rainwater gets in the clay in the soil, and clay expands. And then when it dries out and everything gets hot, it shrinks, and you get these like geometric kind of patterns. It's not circles, it's more like hexagons or octagons. And that's just the way the physics works as the top layer of mud starts to dry out and your clay minerals start to shrink up. And so the same thing happens in lava or magma. If you have a big flow of lava or magma, and it takes a long time to cool down, as it cools down, it's going to shrink just because of heat and density. And so as it shrinks, if it happens in a certain way over a certain amount of time, you can get these fractures that happen and these geometric patterns. And so I think the most famous one, I believe, is in Ireland, or it could be Scotland, but I think it's Ireland. And I believe it's called the Giant's Causeway. And it's basically like this could be a picture of it. It might also be somewhere else. But it's all these columns, and they're all like kind of hexagonal. And because of erosion and weathering, they're all kind of different shapes. So it kind of looks like a weird cubert video game area, but it's nice and neat. And if you get a chance to visit one, again, visit one. Maybe one day y'all go on nice vacations and you're like, ooh, look at that rock. That's a pretty cool rock. That's pretty interesting. How did that happen? I remember. But maybe not. It's okay if you don't. Just enjoy the beach and or the nice rainy Ireland weather if you're in Ireland. So they go through some of the terms we've already covered a little bit. Your large intrusive bodies include batholiths. Batholiths are linear masses of felsic rock, hundreds of kilometers long, so very, very big, large kind of intrusions into the earth. Stocks are surface exposures that are smaller than 100 kilometers squared. And then laccoliths lift the sedimentary strata that they penetrate. So we saw that actually back there at the diagram. Oh, I must have passed it. There it is. So this is the laccolith. It kind of comes up, and like a dike, it goes in between layers, but there's so much material that it actually lifts the layers above it and kind of causes this bulge in the subsurface. That's going to be a laccolith. Okay, and then yeah, we went over those. Laccolith, Mount Ellen. I feel like Mount Ellen is in Washington, but I might be wrong. But in Mount Ellen, nope, Utah. I was wrong. And the Henry Mountains in Utah, and they have a big stock that makes up Mount Ellen. They have this nice laccolith off to the side, and you can see the layers above it that it did push up are eroded away now, exposing the igneous rock, but you have sedimentary rock on either side of it. And then they have a couple dikes and sills mapped out that you could go visit if you wanted to. So what are the characteristics of intrusive igneous structures? They cool within the crust and displace existing rock, and they're exposed by uplift and erosion. And that's the intrusive part. They're intrusive, so they never come out as lava. They're not volcanoes. They're going to cool underneath the ground, and then something else has to expose them. Either they get pushed up by other igneous activity or plate tectonics, or they get the top that's covering them up eroded away. Now, partial melting and the origin of magma, and we're getting pretty close to the end here. So the Earth's mantle and crust are composed primarily of solid rock. The rock is composed of a variety of minerals with different melting points, and we talked about that with Bowen's sequence about how different elements and different minerals melt at different temperatures, and so you get a variety of different elements based on how it's melting and how your magma kind of evolved. Incomplete melting of rocks is called partial melting. And so they have this geothermal gradient, and there is one, I don't know if I asked you to do it or not on the plate tectonics assignment. I might have omitted it. I don't think I did, though. They have a chart similar to this with your geothermal gradient, and then they have another chart that shows your oceanic crust being subducted, and they kind of ask you some questions about whether the oceanic crust is melting, at what depth is it melting, and what could kind of be your effects from that. So just kind of keep an eye out for that one. But on this chart, you have depth in kilometers. On this side, you have pressure. So you see that your pressure increases with your depth. And then you have your temperature gradient across the top. And so you're just seeing that with low depth and low temperature, you have solid rock. As you increase the temperature and the depth, you get partial melting. So you're starting to get some things melting, which will be like your peridotite plus basaltic melt. And then if you go high temperature or high pressure and depth, you get complete melting. And so you can kind of estimate what your depth is going to be, what your temperature is going to be, and figure out if your rock is fully solid, completely melted, or somewhere in between with your partial melting. Now, the geothermal gradient averages 25 degrees Celsius per kilometer. So they're basically saying from the surface, for every kilometer that you go down, you're going to increase 25 degrees Celsius. And that's actually one of the things that we run into sometimes when we're drilling deep oil wells for oil and gas, or if we're trying to drill very, very deep wells for scientific purposes. The temperature rises so much that it messes up our instrumentation, not just the drill bits themselves, but today we use technology to control which direction we're drilling and know the depth and all sorts of other things. And the instrumentation just can't take the heat. And also the pressure increases. They're going to talk about the melting temperature, but the pressure increases as you drill down further, which makes it difficult for your hole to kind of stay open. As you're drilling, if you have to pull your drill bit out, the hole can collapse sometimes. And so that's why with oil and gas drilling, we have to stick like metal shell casing down inside. They call it casing, and how you case it and how you cement it in greatly factors into how well your well is going to do. So yeah, so your geothermal gradient, you get hotter and hotter and hotter the deeper you go. The mantle is solid under normal conditions, which we know because of the way seismic waves travel through it. Hello? Yes. Yeah, no problem. All right. Miss Jones would like to see you. Yeah, and then your pressure increases your melting temperature, just like with anything. The more pressure you have, the easier it's going to be to melt something. Decompression melting is a kind of a different thing. Decompression melting is triggered when combining pressure decreases, and this is usually when so actually I said it backwards. Increased pressure increases your melting temperature, which makes it harder to melt, which is why the inner core is solid, because it doesn't allow your molecules to move around in a fluid manner because there's so much pressure. And so when you release that pressure, obviously not like the inner core, but as your mantle comes to the surface, when you release that pressure, it allows the molecules to move more freely. It puts the melting temperature lower, and instantly things can kind of start to melt. And so decompression melting is triggered when confining pressure decreases. You don't really need an increase in temperature. If the pressure decreases, you can start to melt pretty quickly at the same temperature that you were at before. So that's kind of what happens at the mid-ocean ridge. As this material flows upward to fill the crack, it loses that pressure. It no longer has everything weighing down on top of it, and you start to get partial melting. And by the time you get up to the surface, you kind of have full melting going on. So that's something that you see at the mid-ocean ridges that kind of fills those cracks and those gaps as everything's spreading apart. Adding water also lowers your melting temperature. So these materials at the very top of oceanic crust are going to be saturated with water. They're always underwater. There's an ocean above them. So as they get subducted underneath the surface, they kind of add water to the very top layer of this rock interaction. And so you get melting that happens off the top of the plate. Not the entire oceanic plate ends up coming up for the volcanoes on land. Just kind of the top layer because of that water content that happens to be in the rocks. What are the major processes that generate magma from solid rock? Partial melting, decompression melting when you release your pressure, melting due to the addition of water because of oceanic rock having a high water content just from being associated with water during its entire existence. And then secondary melting via heat from pooled mantle derived magma. So you can kind of get a secondary melting event, just kind of piggybacking off the heat of already melted stuff. Now, the very end, we've only got a couple slides left. We can finish it out, right? Yeah, we got a couple minutes. So, most volcanoes are found near the Ring of Fire. I like their nice font there. Around the Pacific Ocean, I've talked about the Ring of Fire plenty. It's basically the entire edge of the Pacific Ocean because you have subducting zones all around here. Your oceanic plate is being subducted underneath continental plate or other pieces of oceanic plate. As it goes down, it melts, and it forms a lot of volcanoes. There are some randomly distributed areas that have volcanoes, but most of the world's volcanoes happen to be around the Ring of Fire. They show you associations with plate tectonics and volcanic activity. Other than hot spots, which are kind of like the odd thing out, you just have this mantle plume upwelling and giving you some volcanic material like Hawaii. Other than that, volcanoes are almost 100% associated with plate tectonics. Where your plates are subducting, where they're moving around, you have volcanoes, and that's just a direct correlation. You have them at your mid-ocean ridges. You have them at your subducting zones for both oceanic, and oceanic continental. And you even have them in continental rift areas where your continents start to tear each other apart. So, yes, plate tectonics and volcanoes heavily associated. We do have some intraplate volcanism. These are your hot spots, just like you have with Hawaii. You also have with Yellowstone, the same type of hot spot coming up and feeding your volcanism that happens in the middle of a plate. They're kind of illustrating Hawaii here with the multiple volcanoes all formed from the same upwelling mantle hotspot and kind of being dragged out across the ocean floor. So 7.2, last slide. 7.12. How does the geographic distribution of volcanoes reflect plate tectonics? They match up pretty nicely. Continental volcanic arcs at convergent plate margins, seamounts along mid-ocean ridges, and then you have some intraplate volcanism over mantle plumes, which isn't really related to plate tectonics, but also confirms plate tectonics because of the movement. We can see that the volcanoes are moving while the mantle plume stays in the same place. So yeah, we finished it up. I'm so proud of us. Wonderful job, everybody. And I don't know if we'll start the next chapter tomorrow. Maybe we will, and I'll give you Friday to work on the homeworks, but we'll see. We'll see how that plays out. So everybody have a nice day. If you watch the video, don't forget to begin work on your chapter 5 and 6 homework. They're not too long, but you want to make sure you get them done before the test because they will greatly help you out on the test. So everybody have a nice day, and I will see you tomorrow. And hopefully no